Okay, back at it again here. Hope you guys are all doing well. I'm doing well here at home, and I'm attempting my first video while my kids are awake, but they're listening to books on tape, so we're going to hope that I make it through this. Talking about 723 is theoretical and experimental probability for the third day. This may be one of my favorite lessons in everything that I teach in geometry, so just so you guys know that, and in general, this is my favorite topic, so all of the probability stuff is pretty cool to work through. So today we are going to be getting into some card stuff. So that's what I'm showing you here is a standard deck of 52 cards. I'm going to get into this a little bit more later, but the images are a lot smaller. So I just wanted you to see that in a deck of 52 cards, and I put a link down here that you guys can go to. You'd have to type it in that kind of talks about the different types of cards. But there are 4 different suits. So you have clubs, you have spades, you have hearts, and you have diamonds, and those go across here. So there's 13 cards in each of those suits. Okay, there are 13 different types of cards. So there's an ace, there's a 2, there's a 3, there's a 4. So if you go down these rows, you end up with those different ones. There's 13 of those. We talk about black versus red. So since there's 52 total divided by 2, there's 26 black cards and there's 26 red cards. We will also talk about face cards. So these are your face cards because every one of them has a face on it, and there are 12 of those versus your non-face cards, there's going to be 40. Just did a simple 52 minus 12 to figure that out. So that's some of the stuff that's going to come up. We'll talk about it more in detail a little bit later, but if you don't know your cards, that's something to kind of learn or maybe just write yourself down some of those notes. Okay. Okay, so getting into this, we're talking about the fundamental counting principle. Recall that if a random process has a sample space of S in which each outcome is equally likely, then the probability of event A is P of A, the number of outcomes in A over the number of outcomes in S. Okay, that's how we can find our probability. In this activity, we're going to focus on counting methods that can help us calculate the number of outcomes in a sample space or an event. So to be able to find this top number or this bottom number, that's what we're going to be working on today. Okay. So first example that we go with is a sandwich example. So suppose a sandwich shop opens and gives the following choices for sandwiches. You get to select a bread and a meat. Okay, so wheat, white, and sub roll, or turkey and ham. Those are your only possibilities. So you can imagine once we do this how large the possibilities are going to be at some place like Subway. But for right now, those are our only possibilities. So drawing a tree diagram, okay, is essentially saying, okay, we're buying a sandwich. Okay, what choice do we have to make? Well, we have to choose our bread first, and there are 3 possible choices for bread. So we have the wheat, we have the white, and we have the sub roll. Okay, once you have chosen that, you then get to choose turkey or ham. So if you went the wheat route, you now are choosing either turkey or ham. If you went the white route, you're also now choosing turkey or ham. And if you went the sub roll route, you're also choosing turkey or ham. So you have to make one of those choices. Okay. What this means is that in total, we have a choice of choosing the wheat and turkey, the wheat and ham. We have the white and turkey. We have the white and ham. We have the sub roll and turkey, or we have the sub roll and ham. Okay. Which is 6 different possible choices that come out there. Okay. So, in order to entice more customers, the shop adds roast beef and salami to the meat choices. Now, how many sandwich choices are there? Explain how you got your answer. So, you could go through and do this. You notice that this is going to get very tedious. Okay. Hopefully, some of you picked up on it. But since there were 3 choices for this, and there were 2 choices for this, and 3 times 2 is equal to 6, you can use that idea. Okay. So, we have to choose our meat. How many choices of meat do we now have? We have wheat, we have white, we have sub roll, we have roast beef, and we have salami. So we have 5 choices of meat. Nope, that would help if I did that correctly. So let's just go back instead of redoing this video. We have 3 choices for bread, and then times, then we're choosing our meat. So we have turkey and ham, 1, 2, and then roast beef and salami, 3, 4. So we have 4 choices for meat. How many sandwich choices are there then? Well, there are 12 sandwich choices total. Okay. And you have the 3 times the 4, so the 3 is the number of bread choices and 4 is the number of meat choices. Okay. Customers ask for more bread choices, so the sandwich shop responds by adding wraps and 7-grain bread to its menu. Okay, so now we have 5 choices of bread and 4 choices of meat. How many different sandwiches can be made? You simply just do 5 times 4, you get to 20 possible sandwiches. Okay. After surveying its customers, the sandwich shop adds the possibility of cheese to the menu. and allows customers to select, now pay attention to this, no cheese, American cheese, or Swiss cheese. How many different sandwiches are possible? So you have 5 bread choices, you have 4 meat choices, and now you have 3 cheese choices. Now this is a little bit tricky for people. Some people want to say 2, but you actually have 3 choices. You can choose to no cheese, American, or Swiss. Okay, so that's 3 choices in there, and that gives us a total of 60 possible sandwiches. Okay, suppose the sandwich shop makes one of each type of these sandwiches. Okay, and you randomly select one of the sandwiches. What's the probability that the sandwich is one of the sandwiches with cheese? Okay, so we're going back to that probability at the top of the page, number of outcomes in A. So we're talking about the probability of one of these having cheese in it. So that's how you could label this. And on top is going to be the number of outcomes that have cheese in it. So what you have to realize is that if we have a choice of no cheese, American cheese, or Swiss cheese, there's 3 different types of cheese choices here. Divide this by 3, that's going to say that 20 of them have no cheese, 20 of American, and 20 of Swiss. Okay. Again, we want to say the randomly selected sandwich has cheese on it, then there are 20, 40 of them. So American and Swiss together is 40 total. Okay. Out of a total of 60 sandwiches. So the number of outcomes in S, the sample space, is 60. Okay. That would include all of the sandwiches. This can be simplified down to 2/3. It can be written as 66.7%. It can be written as 0.67. Remember, you can tell these in fractions, decimals, percents, lots of different things. So however you want to go through that. Okay, so question 1 provides an example of what's called the fundamental counting principle. So here's the next thing that I'm highlighting in here. We have that fundamental counting principle. And what this essentially just says is that given 2 choices, suppose there's m ways of choosing the first things and n ways of choosing the second thing, then the total number of choices sequence is m times n. If you flip your page, number 2 then says, as demonstrated by your work in question 1, the fundamental counting principle can be extended to a sequence of 3 choices, express that so that it applies to a sequence of 3 choices. So however you want to do it, what it essentially is it's m times n times whatever you want to make this. I just made it p. Okay. So you could go to 4 choices times O, 5 choices times X, whatever you want to make it. You just keep multiplying to get the number of possible ways. So if you think about Subway, for instance, you get all kinds of different things that happen because not only do you choose a bread, but then you choose a meat, but then you might choose another meat. Okay. You might even choose a third meat. You never even know. You have to choose some different veggies. There are so many different options, and you would have to go through a lot of different math to get to that. It's beyond our capabilities right now. Okay. So this is where it gets fun. I love cards. I don't know about you guys. I usually have some students that don't know their cards and some students that do. So this is where we're getting into the cards. You can see I put this down here kind of small just so I can refer to it as we're going through this problem. Okay, number 3, consider a well-shuffled standard deck consisting of 52 cards. So what this statement gives us is a randomness to this. Okay, Caleb is asked to draw a card from the deck, record his result in the space below, then replace the card back in the deck and reshuffle. Okay, so there's some important information here. He's going to draw one card, record the result, and then replace that card back into the deck and reshuffle. Okay, the reshuffling gives the randomness again. He then repeats this process until 5 cards have been drawn from the deck and recorded in the spaces below. Because of the replacement, it is possible for Caleb to draw the same card more than once. Caleb does not rearrange the cards he has picked. So he has first card, second card, third card, fourth card, fifth card. We're not rearranging these. Okay. So it says how many possible outcomes are there for Caleb? So what you have to realize is how many ways are there to draw card number 1. So you have the deck. It's fanned out for you. There are 52 cards in that deck. You draw one of those cards. So we're not putting a 1 here. This is how many options do I have for the first card. Okay. And then I put that card back. I reshuffle. So when I go to draw a card number 2, I still have 52 options in there. Okay. Same thing with card number 3, same thing with card number 4, same thing with card number 5. There are 52 options every time that I go to make that choice. So how many possible outcomes are there for Caleb? You're going to go ahead and multiply 52 times 52 times 52 times 52 times 52, which is also 52 to the 5th power. Okay. Use your calculators, your handy dandy calculators. Use them to the best of your ability. Oh, it would help me if I had a calculator up. So you do 52 to the 5th power, and you're going to get a fairly large number. Okay, now with all of these, we're going to get some large numbers. Okay, you need to make sure to write them down with your commas so you kind of have an idea of where you're at. So we would have gotten 380, 204, 032. Work your way backwards. So three numbers, a comma, three numbers, a comma. So this is 380 million. Okay. Different possible ways that you could have drawn those 5 cards. Of those possible outcomes, how many outcomes have Caleb drawing all hearts? Okay. So we're going back to this idea here. I changed my color here, so I'm in blue. Okay. And we're saying, okay, what do we have as a possibility here? So here, if I want to draw a heart, I have 13 hearts. So your hearts are one of these lines of cards, ace through king. Okay, there are 13 of them. So I have 13 cards I could possibly draw right here. If I wanted to for sure draw a heart, I want my card to be a heart. Okay, you replaced the card so it went back in the deck, which means I still have 13 here. I have 13 in the third spot, 13 in the fourth spot, 13 in the fifth spot. Okay, so to find this number right here, you do 13 to the fifth. I'm not going to type all of these in the calculator. I have them here. You can do it in your calculator, but you get 371,293 possibilities. This is possible ways of him drawing all hearts. This is not saying, well, what if he didn't draw a heart here? This is saying, we're saying he does. How many ways can we do that? Okay, because now is where we're going to talk about what's the probability that he drew all hearts. Okay, so the probability of hearts, and we're going back to that probability model that's on the very top of the 723 notes, okay, is the number of outcomes in A over the number of outcomes in S. Okay, so number of outcomes in A, which is all hearts here, is that 371,293 out of the number of outcomes in the sample space, which is all of the cards, is this number here. So 380,204,032. And if you divide those out, you actually do get a fraction that's decent here. You get 1 out of 1,024 if you wanted to give it as a fraction. It is approximately 0.000, there's 3 zeros, 977. Or you can give it as a percent, which in this case, if you move that decimal twice and then you round, is you get 0.1% chance. So is this very likely? The answer is absolutely not. Okay, 0.1% chance is what we have there. Okay, moving on to number 4, we have another card game, and it's essentially the exact same thing, but there's a big difference here. Okay, a well-shuffled standard deck, so it's random. Juan is asked to draw a card from the deck, record his result in the space below, but not replace the card he drew. And I would suggest that you highlight or darken in those 2 places because that's the big difference here. Okay, everything else is the same. So how many possible outcomes? There are 52 cards when he draws his first card. Okay, he is not replacing the card he drew. So he just drew a card. It doesn't matter which card, but now there are 51 cards. So when you draw card number 2, there are only 51 cards available. When you draw card number 3, you've now taken another card out. So there are 50 cards available, and you keep that process going. So you do 52 times 51 times 50 times 49 times 48, and this gives you 311,875,200. So maybe you had an idea on that one. It's not as small compared to number 3A as maybe some of you would think, but it's still quite a bit smaller. Okay, it's almost, it's about 70,000 smaller, or 70 million smaller. There we go. Of those possible outcomes, how many of them have him drawing all hearts? Okay, so we go back to that 13. There's 13 hearts in here. Okay, so we want to draw all hearts. How many chances does he have at hearts in this first one? He has 13. Now, we didn't replace the card, and we know we want him to draw all hearts, so we're assuming he drew a heart here, which means there are now only 12 hearts left. We are assuming you drew a heart here. There's only 11 hearts left, assuming a heart's drawn here, 10 hearts left, and assuming a heart's drawn there, 9 hearts left. If you do 13 times 12 times 11 times 10 times 9, you get 154,440. Okay, more than half as much. Okay, or less than half as much. Okay, so the probability that he had drawn all hearts, okay, again, we're back to that probability, is going to be that 154,440 over that 311 million. And if you solve this out, it doesn't come out to a great fraction, 33 over 66,640. Have fun with all these numbers here, which is approximately 0. There's 3 zeros there, 495, which comes out as a percent. So I'm going to move that decimal over twice. Okay, if I want to round this, it comes out to a percent as 0.05%. It's actually less likely for this to happen than it is for the other to happen. Okay, so if you did not replace the card, it's less likely. If we keep moving along here, number 5, we get into a jar of jelly beans here. Okay, so a jar contains 6 jelly beans total. We have 1 red jelly bean. We have, yes, I'm going to use my colors here. We have 1 yellow jelly bean. We have 1 green jelly bean. We have 1 black jelly bean. We have 1 pink jelly bean and 1 blue jelly bean. Okay, so we have all of our different colors there. If all of the jelly beans are removed from the jar and placed in a row, how many different arrangements are possible? Okay, so what this comes down to is you're saying, okay, I'm taking a jelly bean, the first jelly bean, and putting it in a row, and then I'm taking another one and putting it down, and there's going to be 6 of them that I'm choosing. Okay, in my first spot, okay, I choose 1, and I have 6 jelly beans in the container, so there are 6 of them to choose from. The possible number of things that I could choose would be 6. Okay, once I've chosen 1 and it says that you're placing them in a row, so you need to read into this and understand there's not going to be a replacement. Once you put that one down, you're not picking it again. Okay, so now once you've picked this one, there's now only 5 jelly beans left, and so therefore there's 5 possibilities for this next one. We don't know which one we picked, but we know that there's one less, so this is just telling us that. And then it's going to keep going down from there until the very last one. You only have 1 chance of picking it, and that's going to be a 1. Okay, if you multiply all of these together, just like the sandwich shop, so just like as if we're picking a bread, we're picking a meat, we're picking a vegetable, we're picking a fruit, we're picking a condiment and a dressing, whatever they happen to be, you're picking each one of those, you multiply them together. This one comes out with 720 different possible arrangements. Okay, only change here is we're going to choose 5 of them instead of 6. So if we have 5 different things that are happening here, right at the beginning, there's 6 of them in the basket. We chose that one. We now have 5, 4, 3, 2. Now, if you multiply all of those, interestingly enough, you get 720. Now, it shouldn't be that interesting because if all you did was take away the times 1 is itself. Okay, so 720 is still our answer there. If we go to 4 jelly beans, okay, we have 4 spots. The first time I choose, I have 6 possibilities. The second time I choose, I have 5, I have 4, and I have 3. Multiply all of those together, you end up with 360. Notice what happened here. Why? Because this was a times 2 that we got rid of, so this is going to be half as much. Okay, letter D, if there's 3, okay, a 6, a 5, and a 4 is what we have. We had 6 in the beginning, we then had 5, we then had 4, okay, and this is going to take us to 120. This is a third as much. Okay, this one was a half as much. This was a third as much because we took away that times 3. And then if we move down to just 2, 6 times 5 is going to give us 30. This is a fourth as much because we took away that times 4. You can see kind of how that's decreasing as you go through there as the possibilities that come out because you're only choosing 2 jelly beans. You're not choosing a whole line of them. Okay, so number 6, based off of that, suppose the jelly beans in question 5 are removed from the jar and placed into a paper cup. So in this case, you are not arranging the jelly beans in any order, but instead are just considering the collection of jelly beans that get put into your cup. How many different cups of jelly beans are possible if 2 jelly beans are removed from the jar and placed into the cup? Keep in mind that putting a green jelly bean into the cup followed by a yellow jelly bean gives the same result as putting a yellow jelly bean into the cup followed by a green jelly bean. In both cases, the cup contains 1 yellow and 1 green jelly bean. Okay, so we just figured out a second ago that if I took and I chose 2 of them, I had 6 times 5, I would end up with 30 possible answers. So the question is this answer 30? And the answer is no, because we just said that yellow and then green is the same as green and then yellow. Okay, now with every color, that's going to be a repeat. So essentially, this I need to take and divide by 2 for the repeats, and that's going to give me a total of 15. Okay, so there's 15 there. Now, how many different cups of jelly beans are possible if 6 jelly beans are removed from the jar and placed into the cup? Okay, the answer is 1. Think about this. You have a red, a yellow, a green, a black, a pink, and a blue. If you pick them, no matter the order, and you put them in the cup, you have to pick every single one of them, and they're in the cup, and it didn't matter the order, you have 1. Okay, there's only one way. All of them are dumped into the cup. Okay. So number 7 then says, try to generalize your results in question 5. Assuming you start with n different colored jelly beans, how many ways can you randomly select K jelly beans and arrange them in a row? So if you start with N jelly beans, okay, so we're saying we're making this prediction. We don't know how many of these we're going to have, okay? If we have N jelly beans to start with, then the next place that we get to, remember, is one less than this. The way that we can write that is N minus 1. The next place that we go is one less than this. So N minus 1 can just be written as N minus 2. Okay, you can keep going from there, N minus 3, and you can keep going. Now, since these are binomials, I'm going to put them in parentheses here. You could put the N in parentheses if you wanted to too. But there's a pattern that keeps going here, and we're going to work all the way down until we do N minus K plus 1. Now, don't worry about that number too much, but essentially you're going to work down until you have none left. Okay. And because you're choosing those as you go. In the scenario from question 6, how many different cups of jelly beans are possible if 3 jelly beans are removed from the jar and placed into the cup? Okay, so from question number 5D, okay, we know with 3 of them we can have 120 different ways. Okay, but this doesn't take into account the different arrangements of the same color. Okay, so now we want to think about, let's say we had a red, we had a blue, and we had a yellow. What are the different ways we could put that together? Well, you could do a red, a yellow, and a blue. So that's if red starts first, you could start with blue, go yellow and red. You could do blue, red, and yellow. Or you could start with yellow and go blue and red, start with yellow and go red and blue. Okay, so there's 6 different ways to put those together. Now, you're not always going to want to do this. So what is the other option here? Okay, the other option here is we're saying essentially how many are the ways to choose these 3 colors. So for red, if you just had these 3, there's 3 ways to choose this one, the next one 2, the next one 1, 3 times 2 times 1 gives you the 6. So this is an easier way to find that number right there. Okay, so this is telling us that there are 6 different arrangements of those 3 colors. There's 6 different ways to put red, blue, and yellow together, and that's the same for any 3 colors you would pick. So we need to take this number and we need to divide by 6, and that gives us a total of 20. Okay, so there are 20 different ways to choose 3 jelly beans and put them into the cup. Okay, different ways. Now, that's a lot of information for today. There is no homework with this. It's just understanding these ideas. But what we're leading to is 2 words, okay? And those are permutations and combinations. And this is what we're going to get into next, okay? Not today, but just to give you a brief look into the future. A permutation is an ordered arrangement, okay? When the order matters, so when you put the jelly beans down in a line, the order mattered, okay? Without replacement from n items, the number of arrangements denoted, you're going to see this symbol, NPK, can be calculated using the following formula. And this formula simplifies down into n factorial over n minus k factorial. Okay. A combination is an unordered selection. So when we took all of the jelly beans and put them in a cup and didn't care about the order, okay, you're going to see this notation of NCK, and it comes into the formula of n factorial over n minus k factorial k factorial, okay? Now, don't worry too much about that right now. You'll always have these notations in front of you, as well as we're going to talk about it on your calculator. You're going to be able to use your calculator for these, okay? But what you do need to know is that a permutation is ordered and that a combination is unordered, okay? So how do we do that? Well, there is a joke. A combination lock. So on your lockers, you have what is called a combination lock, okay? It should actually be called a permutation lock because it does matter the order you put your numbers in. Okay, a true combination lock would accept 10, 17, 23, 23, 17, 10, any combination of those that you wanted to. That's a combination lock. So technically the lock on your locker is wrong and it should be called a permutation lock. The order matters. If that helps, great. If it doesn't, just memorize one of these. Permutation order matters, combination order doesn't matter. And that's all I have for you guys for today. So hopefully you got through that. That's all you have, nothing else to do. So, and I will see you on Friday.